Hi, I'm Anil Kank. I'll be presenting our CVPR work on condensing CNNs with partial differential equations. Here is a typical discrete CNN. It repeats the same digital block many times. These repetitions are computationally and storage-wise expensive. For example, ResNets repeat the bottleneck block, while EfficientNet and MobileNet repeat the inverted residual block. In contrast to discrete CNNs, typical ODE CNN downsamples the input to a very small size and then solve an ODE. This results in less storage, but requires more compute, and more importantly, these do not scale to large datasets. MDEC scales the ODE-CNNs for large datasets by solving multiple ODEs, each at different resolution. But this scale comes with a significant computational cost. For example, MDEC requires significantly large multiply addition operations to achieve decent performance on ImageNet. Our proposal is to replace the repetitions in a discrete CNN with global layers based on PDEs. In this network, we replace the residual block repetitions with global layers that solve a PDE. Such layers result in shallow networks that have low storage and compute footprint. In addition, this layer is easily integrable in any network. A closer look at the PDE is the advection diffusion process, which treats pixels as particles. It takes input feature map I and transforms it through nonlinear function f. This nonlinear transformation is used to initialize the PDE with h0 as the particle concentration at iteration 0. Each particle now has a velocity v, and it allows neighborhood interaction via diffusion process which has a coefficient d. Output of this iteration is that the blue particles have now moved to their new locations, while some of them have diffused to combine into heavier particles such as these purple highlighted ones, while there are extra particles such as the orange ones which got added by the input source Fi. This process is repeated for k iterations, and the final state is the output feature map. We solve this PDE per channel. As a sneak preview, we use a tiny network to visualize the feature maps of various backbones and MNIST. Here are the features for the digit 3 for convolution and residual backbones. It's very clear that both convolutional and residual features are very confusing, and their highlighted regions do not clearly identify the features of digit 3. And these can easily misclassify the input as digit 5, 6, or 8. In contrast, PDE features are very distinctive and clearly highlights the various curves in the digit 3. This is also backed by the test accuracy and the confusion between digit 3 and 5. On Cipher 10, as compared to ResNet and MDEC, our architecture results in significant reduction in model footprint, such as storage, compute, and inference time, without significant loss in performance. We can easily integrate the global PDE layer in various architectures such as DenseNet and DARTs in addition to ResNets. On Cipher 10 datasets, to achieve similar accuracy, global CNNs use 2 to 5x less compute and storage as compared to their discrete counterparts. Similarly, at same computational budget, global CNNs achieve up to 5% higher accuracy. This gap increases to 10% on tiny IoT models. Finally, the proposed architecture scales easily to ImageNet and achieves up to 2x less storage and compute footprint without significant loss in accuracy. To summarize, without loss of accuracy, global CNNs offer storage as well as compute reduction. In addition, they scale easily to larger datasets. Thank you for listening to the talk. Please visit our poster for more details and check out our implementation at the following GitHub repository.